So we are now recording. Allow me to present my screen first. Okay, there you go. Good morning, grade 12 STEM B. How are you, class? I hope everyone is doing well. I know some of you are having a hard time during this pandemic, but keep going and continue striving. So before we begin the class, we will first have an opening prayer. Okay, Miss Karen, can you lead a prayer? Okay, thank you very much. Amen. Once again, good morning, class. So before we start, let me first check my connection. Am I audible to you? Or can you see my screen? Alright, perfect. Thank you for the responses. So for those who can turn on their cameras, please do so. I just want to see the beautiful faces of everyone. But for those who cannot, well, it's okay. Oh, there you go. I'm now seeing your faces. It's great. It's great to see every one of you. So let's have our attendance. Kindly say present if you are here. And for those who cannot open their microphones, you can comment on the chat box so that I can recognize you. Okay, let me start. Di makulangan, Karen. Okay, there you are. Ilaw, CJ. Okay. Magbuo, Baby Jane. Okay. And lastly, Voldemort, RJ. Alright, I'm glad to know that you are all present here today. So let's have a virtual clap for everyone. So let me present to you our virtual classroom rules. Please show up at the correct time and stay in the meet for the entire time. Find a quiet place away from distractions. Mute your microphone until you are called upon to speak. And if you are called upon to speak, unmute your microphone so we can hear you. If you have questions, put it in the chat box or use the raise hand button. And lastly, always be respectful. Class, is that clear? Okay, thank you very much. So now, let's proceed to the topic that we're going to delve on for today's class. But before that, let's have an icebreaker regarding our topic, and we will call it the Guess Who Challenge. So for the mechanics of the game, for each item, a picture of a scientist will be shown, and you are going to guess who that scientist is. Below the picture are the tiles which corresponds to the letters that will form the name of that scientist. But don't you worry, some of the letters are already given so that you have clues to guess the name. I will give you, class, a few seconds to guess the name. Then after that, I will reveal the correct answer. Is that clear? Are you ready, class? I think everyone is ready, so let's proceed to the game. Okay, this is our first picture. You have 5 seconds to guess the name of the scientist. Okay, the timer starts now. Okay, time is up. Mr. Voldemort, you're raising your hand. What's your answer? Okay, let's see if your answer is correct. That's correct. It's Ralph Fowler. Okay, for the next picture, again, you have 5 seconds to guess the name. Timer starts now. Okay, time is up. Miss Magbo, what's your answer? Okay, let's see if your answer is correct. Okay, your answer is correct. It's Rudolph Clausius. And for the last picture, again, you have 5 seconds to guess the name of the scientist. Timer starts now. Okay, time is up. Okay, Mr. Ilaw, what's your answer? Okay, let's see if your answer is correct. That's right. Your answer is correct. It's Julius Robert Mayer. So thank you very much for your active participation. I hope that you can sustain that kind of energy until the end of the discussion. And later, we will encounter these people and their contributions regarding the laws of thermodynamics. So now let's proceed to the discussion proper. So welcome to Thermodynamics Laboratory class. For today's topic, we're going to tackle the laws of thermodynamics. Thermodynamics laws define the fundamental physical quantities like energy, temperature, and entropy that characterize thermodynamic systems at thermal equilibrium. These thermodynamics laws represents how these quantities behave under various circumstances. So how many laws of thermodynamics are there? Do you have any idea? Okay, that's correct. There are four laws of thermodynamics. The zeroth law of thermodynamics, the first law of thermodynamics, the second law of thermodynamics, the third law of thermodynamics. But now, the main focus of our topics are just the zeroth, the first, and the second law of thermodynamics. So in the next few sections, we will discuss each of the laws of thermodynamics in detail. The zeroth law of thermodynamics is one of the four laws of thermodynamics. The credit for formulating the law goes to Ralph H. Fowler. Take note that class. Interestingly, the zeroth law of thermodynamics was actually developed much later than the original three laws. However, there was some confusion regarding the nomenclature, whether should be named the fourth law or some other name. The complication arose because the new law gave a much clearer definition of temperature and basically replaced what the other three laws had to state. So finally, Fowler came up with the name to end this conflict. The zeroth law of thermodynamics frames an idea of temperature as an indicator of thermal equilibrium. So later, you will find out why. By the way, do you have any idea what temperature is? Yes, baby Jane. Yes, that's correct. Yes, it is a quantitative and a relative measure of hotness and coldness. But let me give you a clear definition of temperature. Well, kindly write it on your notes. Temperature is a measure of its average molecular energy. So I hope that is clear to you, class. Okay, the zeroth law. So why is it called the zeroth law? Do you have any idea, Miss Dimakulangan? Well, it's alright. So there is a very interesting story about calling the zeroth law. In the 18th century, few scientists were realized another law should be there apart from three thermodynamics laws to complete the concept. At the same time, Ralph H. Fowler invented a new law of thermodynamics, and this new law represents a formal definition of temperature. It relates all three laws and it should be placed in the first position. So there was a confusion since all other laws are already placed in first, second, and third position. Finally, Ralph H. Fowler came up with the zeroth law idea to avert confusion, so this law was established as the zeroth law. So the zeroth law of thermodynamics states that if two bodies are individually in equilibrium with a separate third body, then the first two bodies are also in thermal equilibrium with each other. So when a body A is in thermal equilibrium with another body, which is B, and also separately in thermal equilibrium with a body C, then body B and C will also be in thermal equilibrium with each other. So this statement defines the zeroth law of thermodynamics. Thermal equilibrium systems are said to be in thermal equilibrium if there is no heat transfer, even if they are in a position to transfer heat. The zeroth law of thermodynamics is totally based on thermal equilibrium. Hence, the basic concept of thermal equilibrium is necessary. While the zeroth law of thermodynamics takes into account that temperature is something worth measuring because it predicts whether the heat will transfer between objects or not. This is true regardless of how the objects interact. Even if two objects are not in physical contact, heat still can flow between them by means of radiation mode of heat transfer. Whereas the zeroth law of thermodynamics states that if if the system are in thermal equilibrium, no heat will take place. Whereas zeroth law of thermodynamics states that if the systems are in thermal equilibrium, no heat flow will take place. So I made here a simple example, which is placing this ice candy inside the refrigerator. So our system 1 will be the refrigerator. The system 2 is this ice candy, and our system 3, which is this plastic. So we can say that the heat transfer involved here is the conduction and convection. Conduction because of the direct contact, and convection because of the air circulation within the refrigerator. So when we are making an ice candy, we will realize that the temperature of this ice candy is the same as the temperature of our fridge after a few minutes or an hour inside the fridge, particularly in the freezer. So as a result, it exemplifies the zeroth law of thermodynamics. So to expound, system 1, which is the ref, and the system 2, which is this ice candy, are not totally in contact. The only thing that links the two systems is the system 3, which is the plastic of the ice candy. So system 3 is the reason why all the systems are in thermal equilibrium. So we have learned that the zeroth law of thermodynamics along explanation and example. So I hope the idea of thermal equilibrium is clear. Okay, the next one is the first law of thermodynamics. So the law of conservation of energy. Energy can neither be created nor destroyed, only converted from one form of energy to another. So the proponent of law of conservation of energy is Julius Robert Mayer. So the first law of thermodynamics, the proponent of first law of thermodynamics is Rudolf Clausius. The first law of thermodynamics is based on the law of conservation of energy, which states that energy cannot be created or destroyed, but can be transferred from one form to another. So the first law of thermodynamics is widely regarded as the easiest to understand because it is an extension of law of conservation of energy. So whatever energy existed at the beginning of the universe will remain at the end. However, thermodynamics is a nuanced subject, and the first law is far from fascinating than this remark suggests. Furthermore, similar to the zeroth law, which provided impetus for the introduction and elaboration of the property temperature, the first law stimulates the introduction and aids in the clarification of the enigmatic concept of energy. And the first law of thermodynamics states that the energy of the universe remains the same. Though it may be exchanged between the system and the surroundings, it can't be created or destroyed. The law basically relates to the changes in energy states due to work and heat transfer. It redefines the conservation of energy concept. So I prepared a simple icebreaker, which is called the Guess the Gibberish. I know many of you are familiar with this game because it was a popular challenge on TikTok and Instagram during the pandemic. So for those who are not familiar with this game, I'll explain to you the mechanics of the game. So, for the mechanics of the game, you have to guess the random word or phrase which pops up on your screen. You have to guess the right phrase, or you are given a few seconds to guess, after which you will be given the right answer to show whether you got it right or wrong. Okay, this is our first word. So you have 5 seconds to guess the word. So timer starts now. Okay, time is up. Miss Magbuo, you're raising your hand. What's your answer? Okay, let's see if your answer is correct. So your answer is correct. It's energy balance. So energy balance. So based on the first law of thermodynamics, energy balance is developed to better understand any process, to facilitate design and control, to identify process improvement needs, and to enable eventual optimization. While the degree of perfection in the process energy utilization or its specific parts allows comparison with the degree of perfection and associated process parameters. So in other similar processes, it is particularly essential to compare current achievable values in the most efficient systems. Priorities can be established for the required optimization attempts for a system or its elements. Such priorities can be implemented based on either excessive energy consumption or an especially low degree of perfection. Okay, our next word, you have 5 seconds. Timer starts now. Okay, time is up. Miss Baby Jane, what's your answer? So let's see if your answer is correct. Okay, your answer is correct. It's cyclic conversion. Well, the first law is used to classify the performance of cyclic conversion systems, such as the fossil-fired steam power cycles or geothermal cycles. Okay, our third word. Okay, you have again 5 seconds. Timer starts now. Okay, time is up. Mr. Elo, you're raising your hand. What's your answer? Okay, let's see if your answer is correct. Your answer is correct. It's change in internal energy. So the change in internal energy of a system equals the difference between the heat taken in or given out by the system and the work done by or on the system. Okay, this is our fourth word. Again, you have 5 seconds. Timer starts now. Okay, time is up. Mr. Valdemar, what's your answer? Okay, let's see if your answer is correct. Answer is correct. It's macroscopic variables. So a change in internal energy causes measurable changes in the system's macroscopic variables such as the pressure, the volume, and the temperature. So the first law describes the relationship between heat transfer, work done, and change in internal energy. So for our last word, you have 5 seconds. Timer starts now. Okay, time is up. Miss Dimakulangan, what's your answer? Okay, let's see if your answer is correct. Your answer is correct. It's limitation. Well, the first law of thermodynamics limitations. According to the law, whenever a system goes through a thermodynamic process, it always maintains a certain energy balance. However, the first law fails to provide the feasibility of the process or state change that the system goes through. The first law, for example, does not explain why heat flows from heat and to cold and when a metallic rod is heated at one end but not the other and vice versa. Well, the first law only quantifies the amount of energy transferred during this process. And the second law of thermodynamics serves as a criterion for the feasibility of various processes. Okay, now let's proceed to the second law of thermodynamics. So I have a question. What led to the introduction of second law of thermodynamics? Okay, yes, CJ? Yes, because of certain limitations. And what do you think is that limitations? Anyone? Okay, Miss Karen. Okay, the first law does not explain the direction of energy flow and its reason. So, for example, it states that the amount of heat lost by a system is equivalent to the heat gained by the surrounding. However, it does not explain whether the heat will always flow from the system to the surrounding or vice versa. Um, the first thermodynamics law established the relationship between heat loss and work done, but it does not mention the source of heat energy and its flow. It states that the energy would be conserved in an isolated system when a change occurs. However, it does not specify the nature of the change. Due to these limitations, the second law of thermodynamics was introduced. So, according to the second law of thermodynamics, any spontaneously occurring process will always result in an increase in the entropy of the universe. So, in layman's terms, the law states that the entropy of an isolated system will never decrease over time. However, when a system is in thermodynamic equilibrium or is undergoing a reversible process, the total entropy of the system and its surroundings remains constant. And the second law of thermodynamics is also referred to as the law of increased entropy. So the second law states clearly and unambiguously that it is impossible to convert heat energy to mechanical energy with 100% efficiency. So why do you think so? Okay, RJ? Yes, there is always some leftover heat in the gas that cannot be used for any other purpose. So let's consider the piston in an engine. The gas is heated to increase its pressure and drive the piston. Even as the piston moves, there is always some leftover heat in the gas that cannot be used for any other purpose. Heat is wasted and must be discarded. So in this case, waste heat is discarded by exhausting the use for the used fuel and air mixture to the atmosphere, or it is transferred to a heat sink in the case of a car engine. Additionally, heat generated from friction that is generally unusable should also be removed from the system. So, second law of thermodynamics. So, in any cyclic process, the entropy will either increase or remain the same. So, when we are talking about the second law of thermodynamics, scientists use a word called the entropy to describe what? Okay, Mr. Valdemar. Okay, yes, it's the degree of freedom or the randomness in a system. So, remember, there are two words in thermodynamics: entropy, which talks about the randomness, and enthalpy, which will be tackled later. So, entropy is a measure of the amount of energy which is unavailable to do work. It is also a measure of the disorder of a system, a measure of the degree of randomness or disorder of a system, and a measure of the simplicity of a system, and it is denoted by a capital S. Since entropy gives information about the evolution of an isolated system with time, it is said to give us the direction of time's arrow. If snapshots of a system at two different times shows one state which is more disordered, then it could be applied that this system came later in time. For an isolated system, the natural course of events takes the system to a more disordered or higher entropy state. And the second law also consider the entropy of a system. Entropy is a measure of the amount of disorder in a system, while a good rule of thumb is the more disorder you have, the more energy you have. Okay, the next is the enthalpy. Okay, what is enthalpy? Okay, yes, Mr. Ilaw. Yes, it is the sum of internal energy and the product of the pressure and volume of a thermodynamic system. Well, what is the symbol? Miss Magbuo. Yes, it is capital H. So I think we're done discussing the laws of thermodynamics. So this is the summary of uh, laws of thermodynamics. So thermodynamics explains how the laws of thermodynamics establish fundamental concepts such as the temperature and heat and the nature of energy itself. And from the sudden expansion or the cooling of hot metal to the unfolding of a thought in our minds and even the course of life itself. Everything is governed by the laws of thermodynamics. The implication of thermodynamic laws more than any other concept have sparked heated discussion about the origins of the universe. Some popular scientific theories are seriously challenged by the laws of thermodynamics. The fact that matter, according to the first law of thermodynamics, cannot be created or destroyed begs the questions of where all matter in the universe came from. Surprisingly, some people dismiss disagreements between the laws of thermodynamics and certain popular scientific theories. While the fundamental laws of matter and energy known as the laws of thermodynamics are used to measure truth in all other disciplines, and some scientists disregard these laws as they apply to their theories. So the laws of thermodynamics lead lead us not only to a greater knowledge of the natural universe, but they point us toward the answers outside of that universe as well. So the asynchronous task for this topic is uploaded in the Google Classroom. So I will transmit the synchronous session recording in your GCR also. So next week, brace yourselves because we will be having a new topic. It is all about heat engine. So good luck kids. Thank you very much and have a blessed weekend and enjoy.